So that's what we're going to see here as well when we do the charts. And you need to always have an E total bar in all of these. I didn't label the columns for you. And we've got possible energies: kinetic, sound, heat, gravitational potential. And so what we've done a lot of these is we haven't included heat. And so if the ball is thrown up in the air and comes back down, we saw that in the other one, no heat is involved here. But this ball does not bounce up as high as it started. And that's because some of the energy has gone towards heat. And we've talked about this a little bit, but I want to emphasize this idea. So here, let's do A, right? A, this one's going to be B, C, this is going to be D and E. So first of all, I'm going to do my total bars because they're super boring. The total bar is 8 the whole way through. And you could do total at first too, but this is kind of what we did on the packet, so it's easy to kind of skip ahead. But this is this crucial idea that the E total cannot change. It stays consistent throughout the entire relationship. We never change our E total. But that means that our energies are going to all have to add up to that E total every time. So what are our energies with this A one? Well, let's go ahead and copy down what we've got here, right? EGP, E kinetic, E sound, E heat. That's all of our energies. So to get in the same order as it was on the homework and on the packet, EGP, EK, EH, I like doing that in red, and ES. That's all of our energies. I'm going to put those in each of these. Boy, that was fast. So I'm going to fill in each of my columns based on how much of that there is. So at A, okay, this is a ball falling, bouncing up and falling again. So right here, I would say it's not falling yet. And it also, it doesn't ask you to draw a velocity vector, but I should have. That's my mistake. The B, right? A, we got no velocity vector. In B, it should be going faster, right? At the point of C, we're going to say that this is before it hits the ground. There's like a little gap here. We never want to say when it's on the ground. That's not very interesting. So right before it hits the ground, it has the most velocity it possibly can. Or if we're saying right after it leaves the ground, it has the most velocity it possibly can. Either way. And then at D, we're back to no velocity or a tiny amount of velocity. And then at E, we're back to velocity, but their velocity is less this time. This is a subtle idea, but this is what happens when a ball, it bounces slower and slower and slower as it bounces to a stop. So let's look at A first. We're going to say this is all gravitational potential energy. No heat has been created, no sound has been created. In fact, any ball that starts to drop is going to be all gravitational potential. By B, have we lost all of our gravitational potential? No, because it's still off the ground. If it was on the ground, maybe we would have lost it all, but it's not yet. So I'm going to say it's about halfway down, so I'm going to put half of the EGP. So what has that EGP turned into? Stuff flying through the air does not create heat or sound, so it must have turned into kinetic energy. I got 1, 2, 3, 4. Uh-oh, I messed this up. This needs to stop right here, and this one needs to stop right here. I got overzealous. 1, 2, 3, 4. It needs to add up to 8. So, cut those off. If you do something like this on the test, like maybe X through it or something, just to make it really clear that you did not mean to take it that far. And this is why pencil is good, right? But I'm using different colored pens so that it's a little easier for you to see. So it needs to be 4 and 4. No heat, no sound yet. All right, so at C, it's all turned into kinetic energy. Now, I'm not going to give you one this complicated on the test. I wanted to go as complicated as I could on the review so that if you understand this, you'll definitely understand the simpler version on the test. You're never going to have the same question again on the test that you had on the review. But the concepts are what's important. So by C, is there any gravitational potential? No. How do I know? It's at the ground. There's no gravitational potential. This has all turned into kinetic. Now I'm going to say all kinetic here because this is right before it bounces. Then when it bounces up and it gets back to here, we've got the same amount of GP as the B did because it's the same height. I know this is hard to kind of piece together, but we want to look at different areas as best we can. 1, 2, 3, 4. Should be the same amount of GP as this one. 4 levels. But now, instead of turning into kinetic, right, it's going real slow. Maybe we say that because it's bouncing forward a little bit, it still has like a little bit of kinetic. Like I'm going to do like 1 box of kinetic because it's moving forward. So what about the rest of the energy? Because this only adds up to 5 and my energy total is 8. Well, it must have turned into heat and sound. And you have some flexibility here on deciding. Do you think the ball creates more sound when it bounces or creates more heat? I really don't mind which one you choose. I'm going to go with our, like rubbing, friction creates a lot of heat and not a lot of sound. But bouncing creates a lot of sound and not a lot of heat. So I'm going to go with like 1 heat and 2 sounds. Why 1 and 2? Well, I needed to add up to 3, 4, 5, 6, 7, 8. I will be nitpicking that, counting, making sure all of these add up to the total. So now when it falls back to E, we're back to no gravitational potential. So it must have sped up again. But I'm going to say that it's not going as fast. It only fell from half the height this time. This is what happens. The ball, as it bounces, the heat and sound takes that energy out. It's still, the total is the same, but there's not as much gravitational or kinetic. So I'm going to go, instead of 4 here, I'm going to go down to like 2 kinetic. Here's another thing I'm going to nitpick. Your heat cannot get smaller, right? Our heat cannot get smaller. We have to create more heat, right? So there's more heat on the bounce, and then this still has to add up to the total here. So more sound as well. It's the only option. This has to add up to 8, and this is 8. So you could have this in a lot of different ways, and it probably is going to look something like this, especially if it's falling. The gravitational is going to turn into kinetic. If it's thrown up in the air, this would kind of be reversed. If we threw it upward, the kinetic would turn into gravitational. We can kind of look at that in the other direction, which is what happened after it bounced. My kinetic that took up in the air turned into gravitational potential and made some heat and sound. And then more heat and sound as it bounces again. So we're going to talk about in the next unit, we can actually look at it as it hits the ground because the kind of energy here is elastic. But that's coming later, so don't worry about that yet. So number 9, explain in words what's happening to the energy after each bounce. What kind of energy is left when the ball finally stops? Energy total is staying the same, as it does. But more and more of the energy is turning into heat. So the original EGP/EK we started with, more and more of it's turning into heat. So when the ball finally stops completely, it's going to all have turned into heat and sound. That's why many bounces, boop, 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 all of it is turned into heat and sound. Okay, I'm going to do 2 versions of this pie graph one for the sled. This first one is going to be the simple version with no heat. We're just going to think about a sled going up and down. We're going to ignore any of the energy that turns into heat. So all of my pie graphs are the same size. I don't need the E total columns like I had above because E total is the size of the pie graph. And it doesn't change. Right? So my slices of the pie, however, will change. And again, I'm doing my simple version first. So these arrows indicate how much velocity it has. So the chunk of pie that goes with kinetic should be equivalent to the size of the arrow. The chunk of pie that goes with EGP, gravitational, should be equivalent to how high off the ground it is. So you might want to start at 1, but I think it's kind of interesting to start at something we know. When something's at the ground, and this is the easiest one, this is all EK, right? It's at the ground level. It's going to go uphill. It's going to gain EK, EG over here and over here, but EK, it's all EK here. So here, it's got a little bit of speed to get started, and then it's going to have more speed as it falls. it's also going to have more gravitational up here and less gravitational down here. The pieces of pi change. Think of the skater. Always think of the skater. It's really crucial. So I'm going to say that this has maybe mostly EGP and then some EK. EGP is more and some EK. If you did this one as half and half, that's okay. But actually, I like this one to be half and half a little bit better. It's halfway down the slope. So it's got about half and half EGP versus EK. And maybe you can make this one even smaller, actually. And if you ever want to do that on the test, you can just kind of, and then you can kind of color this in and say this is all EGP. Just a little bit of EK. Then more EK as it falls, still half the EGP. Why is there no EGP pi slice here? Well, because it's on the ground. And also look at our EK. As our arrow gets bigger, our slice of pi for EK gets bigger. All right, so now our arrow is getting smaller again. In fact, this 2 and this 4 are at the same level with about the same size arrow. So EGP, EK. And then up top here, we didn't quite get to the same level as we got up here, so we're not going to have as much EGP. It's hard to tell, but if we kind of trace across, this is a little higher. So I'm going to say less EGP than I had before. I'm going to go back to what I had originally, and just a little bit of EK. But it's at a lower height, so it's going a little faster. The version of this with heat looks a little differently. Now, if heat is present, we are going to, a little bit of our pi, more and more of it each time, is going to have turned into heat. Our pi graph for heat, whenever we're talking about friction, always gets bigger. It cannot get smaller. There's no way to turn heat back into another kind of energy. So similar ideas here, except now we've got maybe half of this is EK and half of this is EGP. And then we'll split this one in, well, not quite in half, right? This one we've got more GP. So I'm going to make this like this and call this all EGP and this little area EK. So you don't need different colors for this, right? We just want to label big sections of our pi.